So the storage system evaluation, what we're trying to do here is look at if we want to run a workflow in parallel in a cloud, we need to have a storage system that can be used to communicate files between different VMs. And so we want to look at which different file systems we can use, how do we deploy them, and what does the performance and cost comparison look like. So there's some issues with this. At the time we did this study, you couldn't use custom kernels in Amazon, so we couldn't deploy, for example, Lustre. There's some file systems we weren't able to get to work, and there were no HPC instances at the time we did this, so we weren't able to compare those. These are the storage systems we did look at. Local disk was what I showed in the previous study. NFS, this configuration used one dedicated node in M1X large to host the file system for some number of worker nodes. PVFS is a parallel stripe file system. We used an older version of this because we couldn't get it to work on Amazon, the newer version. GlusterFS, this is a distributed file system. We used it in two configurations. Both configurations used the worker nodes as both hosting the file system and running computational tasks. One configuration directed all writes to local disk, but reads were sort of from any node. And then the other mode was distribute, where the file name is hashed, and the files are always sent to the node that they hash to and read from the node that they hash to. And then finally, S3, this is this object-based storage system that Amazon has. It's a non-POSIX, unlike the other systems. It doesn't have a POSIX interface, so it required us to do some changes to Pegasus. We also implemented caching because one thing that's good about workflows is they typically have these write once semantics. So once you write a data file, you never read it again, so you can really aggressively cache, and you don't have to worry about consistency issues. So here's performance montage comparison. The important thing, I guess, to see here is that sort of GlusterFS did the best by far for this application. One thing about S3 was that it didn't do nearly as well because of the characteristics of montage, which is it has a large number of pretty small files. And the latency of S3 is enough that for accessing this large number of small files, it just doesn't perform as well as having a regular POSIX file system. For broadband, this is the memory-intensive application. Again, this application actually did pretty well on Amazon S3 because it reuses a lot of files. The files are larger and there are fewer of them, and reuse a lot. So the caching that we implemented for S3 really helped the performance and actually did better than the GlusterFS configurations here. This is Epigenome. This is a CPU-bound application, and I guess as you would expect, the choice of file system didn't really make a large difference in the performance there. Here's the cost. It basically follows what you would expect. The interesting thing about this is that increasing the performance by adding extra nodes is never going to decrease the cost, because in order for that to happen, you would have to have sort of this super linear scaling, which you're never going to get. So by adding nodes, you're just adding cost onto the workflow. So if you need to get your application done in a certain amount of time, and you're willing to pay for it, then you can do it. But the most cost-effective way is to run it on as few nodes as you can. So here's a case study. This is image Mosaic service. This is hosted by IPAC over at Caltech. And this is using that montage workflow. And so what this is a portal that allows a user to go in, enter some parameters for an area of the sky that they would like to create a mosaic of, and then in the background, it runs a workflow, produces this image that they can download. And so their question was, they're hosting this now on their own resources, on their own cluster. They wanted to know what is more cost effective? Is it going to be more cost effective for us to offload this to the cloud, or should we keep it in-house? And so they're looking at, since they're hosting this currently, they have a really good idea of what the workload is like, how much data is involved, how many requests they get, and they wanted to look at the sort of 3-year operating cost. And we assume that the management costs, the administrative costs are the same for both, because like I said a couple times, and like Lavanya said, you still have to do administration. Even if you put it in the cloud, you still have to manage the software yourself. And so here's the result. And we looked at, so this on the top is the local cost, what they're currently paying. This is using Amazon EBS as storage and Amazon S3 as storage on this side. So it turns out that storage is the primary cost component in the cloud. In the EBS case, it costs $36,000. This is to store the 2-mass data set, which is about 10 terabytes. It costs about $36,000 over 3 years. And Amazon S3, depending on whether you use reduced redundancy storage, it's about the same, or it's up to $55,000. So basically, the Amazon cost for this service is about twice what it costs them to host it locally. So in the case of where you have an application that's using resources over a long period of time, it's probably more cost effective to host them in-house. Here's another case study, another application. This one is Periodograms. These are basically looking at light curves from stars, from images of stars, and trying to identify periodic dips that occur in the brightness of the star due to transiting planets. So this is exoplanets, basically. And so Instead, at IPAC, developed this Periodograms tool that can look at a lot of these light curves and produce these periodograms which identify, a peak where a transiting planet occurs. And so what we looked at was, this is a short-term application where what they want to do is they want to create an atlas of periodograms by processing all of the data that was released by the Kepler project. Kepler is a satellite that's taking pictures over time of a section of the sky and recording these light curves. So what they want to do is create an atlas of periodograms that scientists can then just look at when they're interested in investigating a particular star. So we did this over 3 runs, and the difference between the 3 runs is that each run is a different workflow using different parameters. And we ran the first two runs on Amazon EC2, and you can see that they're on the order of about 1,000 CPU hours in size, and on the order of 100 gigabytes output size. So these are pretty reasonable. We paid about $100 to $100 to $200 to run this scale of workflow. And so after we did these, they came back and said, well, we want to run another parameter set, but it's going to up the resource requirements, right? So this run, run number 3, it required about 50,000 CPU hours. So there's a big gap here between these two. And we didn't run it on Amazon because if you see, the cost we estimated to be around $5,000. And this is not, 50,000 hours is as far as large-scale scientific application go, it's not too huge. But the budget for doing this is not easy, right? So at $100 you can charge it to your project. At $5,000 now you have to start budgeting for it. And at that level, it's easier just to go out and get an allocation on Exceed and run your application there than it is to worry about allocating funds to do it on Amazon. So in the case of this application, for smaller scale, Amazon works great. But for larger scale, it's easier to use alternatives. And Science Clouds may be a solution to that, where you get the best of both worlds. You get sort of service units-based allocations with cloud infrastructure cloud technology.